So today's topic is about searching and sorting techniques. So in searching we'll be seeing linear search and binary search, and in sorting we have several sorting techniques. We'll be seeing bubble sort and selection sort if we have time. So what is the problem we are going for searching? So if you are having a multiple records and you need to search for a particular desired record, and there comes a problem if the number of records available is too large. So what you are trying to do here is we are trying to find a technique which is more efficient in manner and having an average time in finding the desired record among the set of records. For example, if you have 700 records and you are searching for your particular number, if it appears in the first 50 or last 50, it is very easy for us to find the record. But if it is in the middle or at the last means and you are traveling from top to bottom, then it will be a very difficult task and time will be more consumed. So in this scatter you'll see the first level basic type of searching technique. So it's which we call it as a serial search, or otherwise it is called a linear search. So what is happening in linear search is the search element will be compared with each and every element in the set. For example, if you have a record of 100 data, then each and every data will be compared for our matching record. If it is match is found, we will stop our process and tell where it is found. Otherwise, it will have to continue with the searching until you find the record. So what will be the pseudocode is very simple. Each and every element of the array will be compared with the desired element, and if the element is found, we will return the index position, or otherwise we will try to continue with our search. So it's so simple. Like if you have n elements, so if you have n elements, then you will have a for loop for I is equal to 0, I less than n, I plus plus, and your search key element is, if you want to search it with the element, then a of I, if it is equal to the target element, they will just return the position. So simple. Else, after coming out of the loop, you will just tell that the search element is not found here. So here capital N is the search key and small element n is the number of elements. Okay, so keep that in mind. So it's a very simple technique. So we'll analyze how searching is done. So what will be the best case, worst case and average case for a linear search? So best case, if my search element is found in the first position itself. So what will be the worst case is, so if you have an array of n elements and after searching all the n elements and I tell that my search key is not found, or if the search key is found at the last position, then we call it as a worst case for the linear search. And what will be the average cases? Assume that if the keys are likely to be in the middle position or in the top 10 records or middle 10 records, then we consider it to be as a average case for the linear search. So this is the generalized version. So the average running time, if you have n elements, then we'll take it as n into n plus 1 by 2. And we'll take it as our serial search is the order of complexity O of n. The next searching technique we are going to see is a binary search. So why we are using binary searches, it will reduce the searching time by nearly half of the time when compared to the linear search. So what happens here is, the only requirement for a binary search is the array should be a sorted array. That is, the input set of elements must be either in the ordered manner or sorted manner, either from smallest to largest or largest to smallest, or either in the sorted manner based on the alphabetical order. So let us first see the pseudocode, how it works. So if you are given with the n elements, we will try to find the mid position among the n elements. For example, if I have 5 elements, in the array, then I will try to find the mid position. So which will be 2.5. I will take it as a ceiling operation, either a 2 or C. So I will take a flooring operation. So I will take 2. So I will find the middle position and I will consider, sorry, it is 3. So I will compare with the middle position. So the array is a sorted array. So the middle element will be compared for my comparison. If it is equal, element will be found, or otherwise my search will be carried out with the topmost element or the bottommost element, because if the middle element is not satisfied, if it is less than, then I will carry out with the topmost part. Okay. If it is greater than the middle element, then my search will be carried out with the bottom half. So let us see an example how it is done. Now I have a array with 7 elements, and my target element that is to be searched is going to be 7. So what I said, we'll search with the middle element. So here the middle element is going to be the third position. So when you find it out, that third position is going to be my middle element. I will compare with 7, and whether it is equal, no, it is not equal. So whether it is less than the midpoint, yes, 7 is less than midpoint. So my search will be carried out with the first half. There is no point in comparing with this part since it is not required. So we will compare with this part alone. So in the remaining part, I will again find the mid position, which is the mid position from the starting position before the mid position with the previous. It's a recursive call. So I will find it as 6, and again I compare whether it is equal, it is not equal, whether it is less than the midpoint, again it is not less than the midpoint, whether it is greater than, yes. Now the search will be carried out only with this, because already we have traveled with this set for our first step, and the second step is, this is the second step set we are going to compare. So in the second set, again I find the mid position. So you have only one position here. So I will be making, and it is equal to midpoint. As it is equal to midpoint, and element will be printed. So you can see here the coding. So if it is middle equal, I'll just say element is found. Else, you can see here I am telling that if it is less than, then it should be the starting position. So what I do is, from the first position till the middle position, I am doing my search. The recursive call has been called. Suppose if the target element is greater than the middle element, from the middle position to the last position, okay, so sorry, from the middle to the last position, we will carry out with the search. So this is how the recursive call is done for binary search. So you can construct an binary search tree for the recursive calls. So you will start from the mid position, and then you will find out the mid position for the left hand side, and this is the mid position for the right hand side. So when 11 is become, the 11 will become the root node. Now we will see only the less than cases alone. So when less than case come, it is 3, 6, 7. The mid value is 6. So you will have 6 here, and to its left you will have 3, and to its right you will have 7. So this is how it is represented using this diagram. So we'll see the search how it is carried out with the binary tree implementation. So you can see 11, the 7, we are going to have the same example. We will take the 7 is going to be searched. So the mid value 11. So first I will compare with the root node. I will check whether it is 11. It is not equal. Now the entire search has to be carried out with the left subtree. So you can see in the diagram in the array and the tree structure. So now again it has to find the mid value. So the mid value will be 6. So 6 will be compared, and again it is not equal. So it has to be carried out. We'll check less than or greater than. It is greater than. So it goes to the right subtree of 6. And it is only node. So you will just compare it and you will find it out. So we'll analyze the binary search technique. So how we find out the worst case and average case and best cases. So best cases, if the target element is found in the mid position, that will be your best case, and the worst cases after traveling towards the leaf node in a binary search tree, it will be a worst case analysis. So the average case will be either in the mid of the depth of the tree. So it will be O of log 2n. Now, do we have any other technique that is better than binary search tree? Yes, we can implement using an hash table. So you will see the average and worst case for a linear search will be of O of n, and the average and linear worst case for the binary search will be O of log 2n. So we have seen two techniques with enough examples for linear search and binary search technique. So next one is we are going to see about sorting. So why do we have to go for sorting? Because sorting has several applications. If you want to search a people, or if you want to find a set of values among 1,000 values, we need to search all the records. If all the records have been sorted, if the number of set of values have been sorted, it is very easier that at one particular point we can tell that my searching is unnecessary to carry on. For example, I have 100 records and I have it is in a sorted manner. It's the age of a particular person or a particular employee. So I am searching for an employee who is below 20. So when I search, I can start from 1 and I can carry till 20. But when the age is getting started with 21, there is no point. I have to search till the end to find the records, because my exact query is up to 20 only. So from 21, doesn't need any other process. So this is the one of the major application why we are going towards the sorting. We have several sorting techniques. Okay, it is one of the each and every technique is best under certain scenarios. So we have to identify which sorting is best for which type of data sets. So the many approaches are there to sort, and it is used for different types of problems. So we'll see one by one. So today we'll be seeing about two techniques. So that is we are going to see about bubble sort and selection sort. So now what will be your problem is you will be given with n elements, and we want to rearrange either in the increasing order or in the decreasing order. So we will be using operators like less than or equal to or greater than for sorting purpose, and we will do our sorting either in the post direction or in the pre direction. So what is post and pre direction means? That is, the sorted elements will be pushed to either one end of the list or to the other end of the list. So that is the major problem we have to consider. So let us see what are the sorting classifications we have. So the classifications are mainly done based on the complexity. So in memory, if you are doing it with the cache, the sorting mainly we'll be doing is with the internal sorting and external sorting. So the internal sortings, we have three types based on their complexity. That is O of n square, O of n log n, and O of n. So O of n square, we have 3 or 4 techniques like bubble sort, selection sort, insertion sort, and cell sort. So why the complexity is O of n square is the original will be compared with the mirror image of the original. That is, if you have an array A, the same A array will be used for its comparison for sorting purpose. So that is why its complexity is O of n square. So we'll see it in bubble sort and selection sort. And what will be the merge sort is n log n, because you will have two sets which will be combined together into a single sorted list. It's a similar fashion, so you will divide it up and then you will merge it up. So that is merge sort. And quick sort is another different type of sorting. So all the sortings which are listed out here are done in the cache. Okay, it will be done in the memory, not on the any other things. So next type of sorting is external sorting. So you will be using an external device to make your sorting process, especially with the magnetic tapes. How magnetic tapes are sorted, that comes under external sorting. So let us see what is bubble sort first. So bubble sort, it's an ordered list of values by repeatedly comparing with the neighboring elements and swapping their positions if necessary. So simple, we will try to find either the largest element or smallest element, and we will be pushing it to the one end of the list. Okay, so it's based on our way of writing the coding. If you want an ascending order, you will be trying to push the largest element to the one end of the list, that is to the bottom. Or if you want in a descending order, you will be pushing the smallest element to the bottom of the list. So we'll see a coding, you will understand how easily it is done. So you can see here, this is the coding. It's most important is this two for loops is more important. And you can see each and every element will be compared. So I'm taking a first for loop with I starting to 0 with all the elements. And j is starting from 1 onwards, that is not from the next element, so it's starting from first element. And you have n minus I, so that means for each iteration of I, the last position will be holding either largest value or smallest value. So how do we decide here? With the based on the condition. So the condition is here is a of j minus 1 is greater than a of j. So a of j minus 1 means I am comparing the first position with the second position. If it is first position is greater than the second position, then it will be swapped. So this swap, how do we do it is, you can write it in another way. You can use a temporary variable. A is equal to a of j minus 1. A of j minus 1 is equal to a of j, and a of j is equal to t. So this you can write it here itself, or you can write it in a separate function. So this is the swap function. So what happens is, if the first position is greater than the second position, it will get swapped. So we'll see how it is working with an example. So let me have an example. So I'm going to sort all these elements. So you understand that a of j minus 1 will be, if it is greater than a of j, then swap should occur, right? So here I is going to be 0. So okay, so for the first j value, j will be starting from here, and as I said before, a of j minus 1 I return. So this is j minus 1. So these two elements will be compared. So simple. If it is 1 means the previous element will be compared. So j will be here means its previous element will be compared for it. If the previous element is greater than, then you will have a swap. So okay. So I will rub all these things. So we will see how it is done. So you can see if it is greater than, it is getting swapped. Now the next j value is going to be 2. So 45 is greater than 12. Yes. So you will have a swap over here. Then 45 is greater than 77. No. So no swap happens here. Then 77 is greater than 101. No. No swap happens here. And 101 is greater than 5. Yes. The swap will happen. So where are the swaps occurred? So I will write down here. So swap is happened between these two elements and these two elements. Then finally with these two elements. So now you can see after the swap, the biggest element is moved to the last position. So now this is the last position which will not be touched. So why it is not being touched? So you can see each and every time the last position will be subtracted from here. Okay. So for next value of I, when I is equal to 1, j can travel from 1 to 5 minus 1 is 4. So up to 4. So j will be traveling only from 1 to 4. That means I cannot access the fifth position. So in this meaning, it is understood that bubble sort is moving the biggest value to the bottom of the list. So let us see the next iteration when I is equal to 1. Okay. So the last position will not be touched. So j will start from here. So every time it will compare with the previous element. If it is greater, a swap will happen. So a swap has occurred between this. Now 35 and 45, there is no swap because 35 is less than 45. No swap happens. 45 is less than 77. No swap happens. But 77 and 5, a swap will occur. So your final elements will be 77 and 5. So the second largest element is pushed into step. When I is getting incremented, j will travel from 1 to n minus 3. So n minus 3 is 5 minus 3 up to 0, 1, 2, 3, 4. Okay, so up to 6. So you will be traveling up to the third position. So we'll see the next iteration. I is equal to 2. So 17, the last two positions you can't access. Now you will check with the same possibility. No swap. No swap. But the 45 will be, you will be having a swap over here. So your final diagram will be swapped with 45. So the third biggest element is moved. Now the search will be carried out only with these parts. So when I is equal to 3, again these two elements will compare. No swap happens. When 35 and 5 have, you will have a swap. So finally you can see this element 35. You will stop the process. Only these two elements are there. And I is equal to 4. A swap happens. and the final element will be 5, 2, 3, 6, and finally your I loop will get terminated because I is from I is 0 to I less than n. Okay, so I less than n means it is not equal to n, it is less than n. So it is 0 to less than n, so that is the for loop. So for I is equal to 0, I less than n, I plus plus. So I will travel from 0 to 4 only. So you will terminate and you can find my array is sorted. So here the coding has two for loops. So hence you will have two for loops here. So I loop starts from 0 and less than n only. So you have one element less than, and j starts from 1 and it is minus of one element less than with subtraction of I. So when you solve it, it becomes O of n square. So simple. The same array is compared with each and every element. So hence the complexity of bubble sort is O of n square or theta of n square. The next sorting is selection sort. So here the selection sort is ordering of values by repeatedly putting a particular value into its final position. So more specifically speaking, you will try to find the smallest value in the list and switch the value with the first position. Then we'll increment to the second position, we'll find the next smallest value and we'll push it into the second position. Then going to the third position, we'll repeat the same procedure, finding the remaining elements among the remaining which is smallest, that will be pushed into the third position. So this is the selection sort. For a example, when you see the coding, you can see here I have a for loop. It starts from 0, I to n. Okay, we'll take this as capital N, and this one is also capital N. Okay, so you can see I have from I loop starting from 0 to n, and j is starting from I plus 1. So it will start from the second position onwards whenever I is. So the first value will be given to a min index. Whenever there is an element, I will compare with j and a of min index. If a of j is smaller than min index, I am not swapping the elements, I am just registering the position to the min index. So this is the most important part. After I am traveling towards the entire list, if the min index will be holding the smallest element, then that will be swapped between the current position and the first position of I. You can see here it is swapped with the first position and with the smallest element position, and the swap will happen. So when you see an example, you will understand it to a very clear position. So now if this is the thing, so initially I will be here and j will start from the second position till this. So in this position, with the remaining elements, I will try to find which is the smallest element. So 1 will be smallest element, so you will have min index over here. So your min index will be here. Now I and min index will get swapped. So you will get swapped. You can see 1 and 3 is getting swapped. Now what will happen in the second is, now I will increment. So I comes to second position. Now j will work only with this part. So because j starts from I plus 1. So from this it will start. It will try to find what is the minimum element among the j. So the minimum element is 2. So that will be recorded in min index, and a swap happens between I and min index. Now the next position is going to be, I will be in third position and j will travel from with these two, and the next minimum value between these j travel cell is going to be the min index. Again a swap happens, 6 and 3 will be substituted, then I will be here, j will be here, no swap is required because it's not equal, so it will be done. So this is how a selection sort works. So I will repeat again. So I will select the first position, its value, and I will try to find the smallest element from the remaining elements. So that's the simplest way you will be doing. So I will be the first selected node, and from the remaining nodes, so from the remaining values, you will try to find the smallest element. So that element will be swapped with the first position and the particular element. From the second node, with the remaining elements after the second position, I will try to find the minimum element and I will swap with this process. So this is what it is represented here. So let us understand how in iteration way it is done. So we'll do it in a iteration fashion. So here I will be is going to be 0. So I use one brown color for I value, and I will be using a green color for min index. So that will hold the index value, not the cell value. And the red color will represent the which are the elements that are going to be compared with the min index values are. So we'll start with the J. Okay, so initially I will be in the 0th position and min index also will be in the 0th position. So I will compare with the remaining elements other than the first position. So 63, 1, 72, 64, everything will be compared. So when it is greater, okay, that is if A of J, that is this element, if it is less than, so I will write it here, if A of J is less than A of min index, then a swap out, then your min index will be updated. So your min index will update. We don't swap it, min index will update with the J value. So we'll check. So 63 is not less than 27, so J will get incremented. It goes to 1. Now 1 is less than 27, so what happens? Your min index is getting updated, right? So we will carry on with the other elements. We'll try to find whether it is done. So next position is third position. 72 is not less than the min index. 64 is not less than min index. So you will always compare with the min index. So it is now 2 is the min index. So it will compare 64 is not less than 1. 58 it is not less than 1. 14 is not less than 1. And 9 is not less than 1. So all the loop is over. So all the 7 elements is done. Now when you, before incrementing the I value, we will swap I and the min index. So when you swap it, what happens? So these two elements will be swapped and one will not be touched again, because when I is incremented, now I will become 1. So the smallest element is pushed to the first position. Now the second smallest element will be pushed to the second position. So we'll see an exam iteration for I is equal to 1. So 1 will not be touched. So I will be here. So it is I will be equal to 1, and min index also initially will be equal to the first position. Now we will compare with the rest of the elements other than the second position, that is second, third, fourth, 5, 6, 7 will be compared. If 27 is less than, min index will be updated. So 27 is less than, so min index is updated. Now the brown color tells that the second position is considered. Now 72 is not less than 27, no updation. 64 is not updated. 58 is not updated, but 14 is less than 27. So what happens is it will be getting updated. So 14 is less than 27, so min index is getting updated, and the next value will be 9. 9 is also less than 14, so 7 will be getting updated. Now we are going to swap between the first position and the 7th position. So swap will happen after the final result will be of this form. Now you'll see the next iteration, I is equal to 2. So that means I will be over here. So I is equal to 2. So rest of the element we are going to consider it for J loop. So 72 is less than 27. No. 64 is not less than. 58 is not less than. But 14 is less than. So we'll get updated with the min index. Then finally, so 14, after 14 update, 63 still it is not updated, so it's not less than 14. So a swap will happen between the second position and the 6th position. So after swapping, 14 will come to the second position and 27 will go to the 6th position. Now we'll see when I is equal to 3. Now your I will be over here, I is equal to 3, and the J loop you have to compare with the remaining elements. So 64, is it less than 72? Yes. So min index will be updated. Again 58 is less than 64. Yes. Again it will be updated. 27 is less than 58. Yes. So it will be updated. And finally 63 will not be less than 27. So a swap happens between the 3rd position and the 6th position. You will have a swap happens here. between 72 and 27. After that, we'll get incremented. So the next iteration is I is equal to 4. So you can see I will be over here, I is equal to 4. The remaining search will be with 5, 6 and 7. So 58 is not less than, okay, less than 64, so it will be getting updated, but 72 and 63 is not going to be less than 58, so there will be no swap. So the swap only happens between the 4th and 5th position. Now 54 and 6 will update and the final element will be done. Now when I is incremented, so we'll be in the 6th position. So 72 and 63 alone will be compared. So only 63 is less than 64, so min index is updated. Swap happens between 5th position and 7th position, and 63 will be moved. And the final element will be also of this form, and swap will happen. And finally, when you come out of the I loop, you can see my loop is sorted. Now let us talk about the running time. So we had two for loops again here. When you have two for loops with for n elements, automatically when you resolve it, it will become O of n square. So the best case and worst case, we don't have a best case and worst case for here. So if the loop for sorting, there is no best case and worst case, only the average running time will be calculated for the sorting techniques. So that's all for today's class. So we have discussed about sorting techniques and searching techniques. In searching, we have done with linear search and binary search, and I have explained bubble sorting and selection sorting. Let us see the other sortings in the next session. Thank you.